Hello everyone, I'm Vaibhav Gupta, and in this video, we'll be going over some very interesting principles of the quantum computing space. So let's get started with the first one, which is the multiverse interpretation of the quantum mechanics. This was given by the scientist Hugh Everett in his PhD thesis in 1957. So what this principle says is, let's say I have a time at one of my axes and three-dimensional space along the axis. So, and I'll define a universe where I have a light source emitting the photons. As we discussed in our previous videos, that the photons can take multiple paths. So let's take path one, and if it takes path one, it goes to this universe. It take path two, it goes to this outcome. It take path three, it goes to this outcome, and so on. And it further branches into different outcomes. So even they can both go to the same outcome. It can have the different outcome. They have, and so on. So this is the snapshot of the multiple outcomes of the universes along the time. And these snapshots exist as a wave function simultaneously as long as it's existing in an isolated system. And they all collapses to one output when we measure this wave function. Measure. So this measurement collapses and destructs my quantum wave function and probabilities to just one outcome. So let's imagine that I have 1,000 particles and each can branch into two different possibilities. So I have around 2 raised to the power 1,000 possibilities. We can't emulate this much probabilities in a classical computer, but for our quantum computers, these all can exist as different universes at the same time. And when we measure that, we can measure the one favorable outcome. So this was our first principle. After that, the second is the quantum entanglement, or as Einstein said, a spooky action at a distance. In this principle, we say that while measuring the multiple qubit systems, some particles are entangled, which means that if we measure the state of one qubit, then the state of the second qubit also collapses to a single state. What I'm trying to say is, let's say I have my wave function this, where of two qubit system with two possibilities, either 0, 0 or 1, 1, and both the possibilities are equally likely. And my qubit is an electron spin qubit. So let's say I have an electron here on Earth, and I take the second electron, which is entangled with the first one, to Pluto. And if I measure my first qubit, and after measuring, it gives me the state 0. So simultaneously, what happens at the same time is my second qubit state collapses to 0. Sorry, but my second qubit state at the same time collapses to 0. So if after the measurement, the result of the state of my first qubit comes out to be 1, then my second qubit will also collapse to 1. And interestingly, it will collapse at the same time, irrespective of how far is it from this particle. So this is what we call quantum entanglement. And now in this system, there's nothing as a state of the separate particle. So this is our second principle. And then the third one, we say that there is no cloning allowed. There's no cloning of the quantum mechanics or the quantum state is allowed. So in the quantum mechanics forbids the creation of the identical copies of an arbitrary unknown quantum state. So what I'm trying to say is, if in one of my isolated system, there's a wave function of a quantum state, I just can't create the identical quantum, the wave function. I can't just copy paste it to a new system, and I can't achieve that same identical quantum state. The second thing it says that when we are running our quantum algorithm and when we are doing the measurement at the end, we can't save the checkpoints of our quantum state in between. What we used to do in our classical systems, which we used to save our intermediate states so that we can do error correction, and if something wrong happens, we can just start from the latest checkpoints. But this principle prevents us from using that classical error correction techniques on the quantum states. We cannot create backup copies of a state in the middle of a quantum computation and use them to correct the subsequent errors. So these were the three basic principles of the quantum computing. In our future videos, we'll be going over the different type of quantum computers, and we'll understand how we can implement different type of algorithms on the quantum computers. So thank you for now, and I'll see you in the next videos.